let's very quickly review what you already know about limits. So here I have some contrasting examples. They're intended to be exactly the same, except in this case, when you evaluate the function at 3, you get the value 2. There it is. Here, it's undefined because there is no value of the f function at 3. So these functions are the same everywhere except at x equals 3, but the limits are the same. So if you say, what's the limit of f of x as x gets closer to 3, and what's the limit of g of x as x gets closer to 3, in both cases, the answer is 1. And so this illustrates the intuitive idea of a limit. The idea is you're trying to describe what value something is getting closer to. So here, we're trying to find the limit of f of x, which just describes the y values in the function. And so we're saying, what's happening with the y values as x gets closer and closer and closer to 3? So this is saying the y values are approaching 1 as the x values are approaching 3. But notice that we don't care what happens when we actually get there. So in your imagination, you don't actually know what's happening at x equals 3. You just want to know where are the y values headed as you get closer to 3 from both sides. Something else you know is that in order for the limit to be defined, the left and the right-hand limits have to be equal. So in this case, the limit as x approaches 3 of f of x equals 2, because the y values from the left and the y values from the right are headed towards the same y value. They're both headed towards 2. In this case, the overall limit does not exist because the left-hand limit, which you write using a little minus sign next to the x value you're approaching. So the left-hand limit in this case equals 2, because as I'm approaching from the negative side, from the left-hand side, the y values approach 2. But the right-hand limit, which you designate with a little plus sign here, the right-hand limit is heading towards 1. So because they're not the same, the overall limit isn't defined. And I mean, that's a kind of formal way of saying it, but it makes sense. If the intuitive idea is you're trying to describe where the y values are approaching, if the y values approach different spots depending on which direction you're headed from, it would make sense that there isn't a single answer to the question, where are the y values approaching? So you'd say it doesn't exist. There is no single place where the y values are approaching because there's two different places. Remember that graphs and tables and equations are all just different representations of the same underlying idea, a functional relationship. So you can use limit language to describe patterns where I give you information from any of those forms. So in this case, we have a table, and you can ask, as n approaches infinity, as n gets bigger and bigger and bigger, is there a particular value that the y values here are approaching? And just kind of by general inspection here, it seems like the answer is probably 0. Here we're just making guesses at what the limits are. You couldn't actually know what the limit was unless you had an equation and you evaluated it more carefully. But certainly from inspection, it looks like as n's getting bigger, f of n is getting smaller and smaller towards 0. It's approaching 0. So the way you'd write that is this way. Finally, you have a little bit of experience evaluating limits algebraically. So here we're asking if x gets closer and closer to 1, what is this expression getting closer and closer to? So like an easy thing to do if you wanted to, well, I mean, it would be labor intensive, is you could plug in values of x that get closer and closer to 1. So you could plug in 0.9 and 0.99 and 0.999. And you'd plug them into this expression and you'd see what's the pattern in the y values. A different idea is you could graph this function and see what the graph looks like. If you use Desmos actually doesn't show you where holes are, but I happen to know this is what the graph looks like. So if you knew this is what the graph looks like, then you could pretty immediately answer this question. The answer is, as x approaches 1, the y value approaches wherever this hole is, the y value of where the hole is. But where's the hole? You have a technique for evaluating this also, and this is probably the best idea. Because these ones you're just approximating. You're just making guesses based on pictures, really. Idea 3 is actually simplify the expression to figure out what's the y value where the hole is. So you may have noticed that you can factor out an x from the numerator, and so now you have x minus 1 dividing itself. But let's think very clearly about what that actually means. You can think about this expression as the same as this expression. All we're doing is we're multiplying x by an expression whose value is always 1, because something divided by itself is always 1. So if you think in terms of a graph, what does this graph look like? It looks like the graph y equals x multiplied by 1, but multiplying by 1 doesn't change it at all. So that's why this line here is y equals x. The only thing that this does is it introduces the discontinuity, because I know that if I plug in x equals 1 to that expression, it will be undefined, and a number times something that's not defined is also not defined. So the only effect at all of doing this multiplication is you're not changing the original function x, you're just punching a hole in it at x equals 1. And this is the same as what we started with originally. So all of this is to say, an easy way of evaluating the limit where there's a hole is you algebraically simplify until you can divide out the expression that was producing the hole. And so you know that the limit should be the same as what would happen if you plugged in the hole. And you plug in the hole if you pretend that this expression didn't exist. So now I can just literally plug in x equals 1, and I can see that the limit here approaches 1. Because that's the y value you'd get if you were able to actually plug in 1 to the original function. Usually you only have to do something tricky if there's a discontinuity. If you have a continuous function and I want to know what's the limit as x approaches something in particular, you can just plug in the x value, figure out what the y value is, and as long as your function is continuous there, you know that the y values are also approaching the y value that you get when you plug in the x value you're getting closer to. So in this particular case, same function, we've still got the discontinuity at x equals 1, but I'm not interested in what's happening as we get closer to 1. I want to know what happens as we get closer to 10. So there's just no problem at all here. I can plug in 10. I get 100 minus 10 over 10 minus 1. So that's 90 over 9. Ta-da! I don't know why I put a box around that one, which simplifies as just 10. So you don't need to do any fancy algebra as long as it's a continuous function at the point that you're trying to evaluate the limit for. You only need to be careful when there's a discontinuity at the value where you're getting closer and trying to find the limit. Okay, your review is complete.